On the other hand, there are many different ways that the boat does not catch the ferry, right? It may just like what we watched, it landed in front of the boat, then it slid off into the ocean. Or it missed the boat just by 100 meters. So there are also many different possibilities that the event A does not happen, right? So basically, you can again think of a different events. I can have an event A. So let's say I can have an event A like that. I can have a different event. Come on. Don't know what happens. I can have a different event B. That's like that. Okay, and so there could be an overlapping region that is both A and B happens, or you can construct two events. You can also have the possibility that A happens but B does not happen, or you can have B happens and A does not happen, or neither A and B happens. You can construct events that are separate, that are completely non-overlapping sets of the subsets of the probability space omega. That would mean I constructed two events that are mutually exclusive, right? It's basically impossible that both A and B happens at the same time. So this is really the basic framework of how does probability theory describe the world in which different possibilities could happen. Okay, so how does that relate to computational method? So in a computational setting, we basically take an input, okay? The input we are going to be taking is no longer going to be a deterministic differential equation, a deterministic initial condition, a deterministic set of parameters. But we are going to be taking a probability distribution, and we are going to be treating, for example, our initial condition as a random variable. We're going to be treating, for example, a parameter of our differential equation as a random variable. And then we are going to be computing the output again as another random variable. So we want to characterize the distribution of our output, right? The output might be a random variable. It might also be an event. We want to characterize the output probabilistically. What does that mean? That means we may want to, for example, if the output is an event, right? If we're interested in the boat catching the ferry or not, that's an event. What we want to characterize is that under the random inputs, which might be a statistical data collection of what the wind condition is on a particular spot in the ocean, right? We want to take that as an input and compute what is the probability that the output actually happens. Or if the output is a random variable, right? For example, you might actually figure out, you might want to figure out, okay, how long does it take for the boat to catch the ferry, right? That's the length of time it takes is a random variable. We may want to quantify what is the probability distribution of that output random variable. What is the mean or average of that random variable? What is the standard deviation of that random variable? These are the characterization of the output we want to get in with a computational method. All right, so let's actually do a little bit more on the random variable and random events. And we want to discuss how do we characterize them. Okay, in a probability space, we not only have the set of all possibilities, we also have a measure of any sets or any events, right? So if you define a probability space, you just have the omega is actually not sufficient. You also need to define what is the probability of any A. So that's basically no, I mean, in probability theory, this is called a probability measure, right? So it measures how big the set A is. If A is big, the bigger the set A is, the higher probability that A would happen. The smaller the set of A is, which means A would happen under less circumstances, right? Under less possibilities, then the probability as a measure, right? That's always between 0 and 1 would be less. Okay, and for example, if you want to get the probability of what's the probability that both A and B happens, that would be the probability of the intersection of A and B, right? That's the probability that both A and B would happen. So this is the P is called the probability measure. All right. Okay. So basically, you take a subset of omega. P would just give me a number between 0 and 1. And there are some conditions that P has to satisfy. For example, if you have a bigger set, P always give a bigger number, etc. If you give the entire set omega, P should be equal to what?
1.
Right? Yeah, that should be equal to 1. And if you give it the empty set, usually like that, it's equal to 0, right? The probability of impossible